Yeah, so I'm gonna talk about reducing the CNOT count in circuits. It's something that I've been experimenting with a bit. And the other thing that's a bit of an experiment is I'm going to give this talk entirely in Python. So we'll see how that goes. So here's a ZX diagram that I've pre-baked. If you want to see the guts of that pre-baking, it looks like this. But I guess if you're not a physics nerd, you don't know what this means. Can everyone see the text? Is it big enough?
Yep.
It's fine for me.
Great. Okay, so here's a ZX diagram, and something that we could do to this diagram is apply the bialgebra rule. Right, so here we see that very typical shape of a red multiplication connected to a green co-multiplication, and we could replace that with a sort of crisscross shape, which is something that physics does. And something that it also does is it will go ahead and fuse the spiders, right? So if I apply a bialgebra here, then I'll end up with 2 green nodes here and 2 red nodes there, and those can get fused into the nodes that are already there. All right, so we can see that happening. We apply a bialgebra, it looks like that. Okay, so there's another thing that's very much like the bialgebra rule called pivoting. The only difference is rather than working with red-green diagrams like this, pivoting works better with green Hadamard diagrams. Okay, so if I take my original graph, so I'm taking this graph, and I call 2GH on it, then what it's going to do is it's going to replace each of these red dots with a green dot surrounded by Hadamard gates. And the way that shows up in physics is as a blue line. So this blue line means that there's a Hadamard gate on that edge. Okay, so now if I apply a pivot, say at the same place, let's see, these numbers are probably too small to see, but this is node 4 and node 5. So I did a bialgebra with 4 and 5 and got here. If I do a pivot with 4 and 5, then I get here, which looks very similar. And in fact, if I just make these green dots red again, you see I exactly get the right-hand side of a bialgebra. Okay, so pivoting, what it accomplishes is it deletes a pair of nodes and then totally connects the neighbors of the first node to the neighbors of the second node. Okay, or at least what we're calling pivoting is that. There's a couple of variations of it. Okay, so that's the kind of basic pivoting rule. There's a very similar rule you can apply if you have pies on these nodes, but effectively you just take a pie and you push it through to the other side and do the same if there's a pie there. And I can do basically the same pivot rule. And this is one of the main simplifications we use in physics. However, here I'm going to take a variation of that graph before. If I have some non-Clifford phases on spiders, then it's not obvious that I could do a pivot there. Okay, so this has a pi by 4 phase, this has a 3 pi by 4 phase. And now if I look in this graph and see if there's any matchings, so see if there's any places I can apply a pivot rule, I get the empty list here, which is physics's way of saying that there's no way I can apply a pivot. But if I sort of deal with this graph a little bit, and I take this node, again, you can't really see it, but that's node 4, and I unfuse it. So what I mean by unfuse is I'm going to put a pair of spiders and a pair of Hadamard gates. Well, actually, you'll see what happens. So if I unfuse 4 and I unfuse 5, I get something like this. Okay, so see, effectively what I've done is I've taken this green spider and I've pulled a bit of it out with the pi by 4 phase, and I've put a pair of Hadamard gates, right? So that pair of Hadamard gates actually would cancel and this fuses back in, and I would get back to here. So that's why I'm calling that unfuse. And now something you'll notice is that I do have a place I can apply a pivot rule, right? I can apply it to these 2 vertices. And if I apply it, I'll get something that looks like this. Okay, and something to notice is before we had spiders here. Call these just normal nodes. We have spiders. And after I apply a pivot, those spiders have turned into phase gadgets. So this kind of shape, I guess probably a lot of people are familiar with it, is called a phase gadget, which is another thing that we use quite a lot in physics. You should think of this whole shape kind of as an atomic thing, which is a bit like a spider. So you see, if I think of these two operations, this unfuse and this pivot, together as a single operation, then what I've done is I've turned a pair of connected spiders into gadgets, and I've sort of shunted some of the edges around them around. Okay, so that's what happens if I have two things that are already spiders, and I do this kind of funky pivot thing. Now suppose I have this kind of thing. So here I have a spider, and it's next door to this, which is a phase gadget. Well, now, if I unfuse just the spider, I get something like this, and again, I have a place I can pivot. I think it's here. I want to pivot. Then a funny thing happens. The thing that used to be a spider is now a gadget, and the thing that used to be a gadget is now a spider. Right? And I can do this with any combination of spiders or gadgets. I apply a pivot, and it will kind of toggle whether the thing is a spider or a gadget. So for instance, if I thought of this as a graph that I was starting with, okay, so now I have a gadget which is connected to a spider. If I unfuse the spider, which is called 10, that's vertex 10. If I unfuse the spider and I pivot, then what I end up with is a spider connected to a gadget, right? So here, gadget, spider, here, spider, gadget. And something you'll notice is if I met this kind of shape in the wild, then doing this pivot is actually a really good idea, because the graph that I ended up with is a lot sparser than the graph that I started with. Okay, so that's the kind of idea that I started playing with a few weeks ago, toward trying to decrease the CNOT count in circuits. So if you've seen our first graph-theoretic simplification paper, actually both papers, we treat both of these effectively as normal forms. So if we got to either of these, we would just stop, and then we would try to extract a circuit and then hope that circuit had a pretty good CNOT count. So I started thinking that actually, if I explore this space of possible normal forms a bit more before extracting a circuit, then I could get something with a lower CNOT count. Okay. So that's what I did. And the way I did it was using some simulated annealing. So I guess probably a lot of people have met something like simulated annealing before. It's an optimization heuristic where you take random moves, and you accept the moves. If your thing is getting simpler, you always accept the moves. And if your thing is getting more complicated, you accept the moves with some probability which goes down as you go. If that explanation didn't make that much sense, it'll probably make more sense when you see it in action. Okay, so here's an example that I'll just go through to show you how I've been using pivoting and annealing together to decrease the CNOT count. So this is just a bit of setup here. Okay, here I'm loading a circuit. This is the Barinko Toffoli 4 circuit. And I've converted it to Clifford plus T because I want to do ZX stuff to it. And now if I have a look at the size of this circuit, you can see that it's actually a relatively good-sized circuit. It has 114 gates. The thing I'm going to be paying attention to throughout this is the 2-qubit gate count. I don't particularly care if they're CNOT gates or say CZs or something, but this number is very important. That's 48 2-qubit gates that I start with. Okay, so our kind of main optimizer in physics, well, one of two main optimizers in physics is full reduce and extract. So what we do is we take a circuit and we convert it to a ZX graph. We call this full reduce thing, which computes one of these normal forms where I can't use pivot and similar rules anymore to get any nodes out. So if I apply full reduce to this thing, I get this, which I like to think of this as the sort of skeleton of that circuit. So it shows basically where the T gates were, or the non-Clifford gates were, and also some kind of connectivity between them. And then from this skeleton, I can extract a circuit, and I get a different circuit. Okay? And you think everything's good, everything's fine. But then if I look at the stats of these two circuits, okay, my original circuit had 48 2-qubit gates. My new circuit has 59 2-qubit gates. Okay, so that was the kind of well, I wouldn't say it was so much of a secret because I think we even admit it in the paper. But this is one of the downsides of this approach is you can actually end up increasing your CNOT count because you might have already been in some kind of minimum and you've jumped out of it in the process of this kind of non-deterministic simplification. Okay, so the way we got around this in the reducing the T count paper was we did something different. Rather than doing a full reduce and extract, we did this other thing called teleport reduce, which I won't really go into the details here, but it actually doesn't do anything to your 2-qubit gates. So if I call teleport reduce, all it will do is decrease the T count without touching the CNOTs. And then if I call this, which is just a basic circuit optimizer, so basically, you know, do gate cancellations wherever you can, then you see that indeed I do decrease the CNOT count. So here I had 48. The teleport reduce gives me 44. Okay, so it can't increase it, and often it does decrease it, mainly because it's getting some T gates out of the way, right? So here there were 56 T gates, and here there are 28. Incidentally, it's the same as the full reduce. There's a good reason for that, which some of you might know already, and I'm happy to discuss that a bit more if people want to know. So anyway, this seems like bad news for full reduce, right? It actually increases the CNOT count. So I started thinking about how I can explore this normal form space using some annealing. So there's this function called pivot anneal, which takes a number of iterations and actually some other parameters, and it will apply random pivots in a kind of simulated annealing kind of way, and try to reduce some cost function. In this case, the default cost function is just the number of edges. So I'll run this and we'll see what happens. Okay, so it's running for 500 iterations, which goes quite quickly. And we'll see what happens is, so the way annealing works is early on, it moves around the space a lot. It's allowed to accept even things which increase the number of edges because we don't want to get stuck in a local minimum. So we start taking random moves and you see the edges go up. This little arrow means it's going up, and there it went down. And we see that things are kind of jumping around quite randomly for a while. And then with annealing, the longer you do it, the less the lower of probability you want to accept things that actually increase the cost. So as we go farther, we'll start accepting these ups less. And then we work for a while, and then by the end we get 86. Okay, so I didn't actually show you we started with 96 edges in the thing, and then we do this kind of simulated annealing stuff, we get down to 86. So we got 10 edges out by kind of walking around the space like this. Okay, so that's good, but edges aren't really the same thing as CNOT. So we should actually try to extract the circuit and see how well this sparsification did. Okay, and if we look, we see here's our original, which had 48 gates. Teleport reduce had 44, full reduce 59. If I do this annealing thing, I go from 59 down to 51. Okay, so not good enough, right? Because 51 is still more than 48, which we started with. Okay, and it's definitely more than 44, which is the previous best known thing that we could do with physics. But as I said, the number of edges is not the same thing as the number of CNOT gates we end up with. So what we can actually do is do annealing with a different cost function. So here I'm going to score the thing by actually extracting the candidate circuit and counting how many CNOTs that circuit has. Okay, so here's another call to pivot anneal. This time I've adjusted the cooling parameter, so that's one of the kind of annealing things you can tweak with. And I've set the score to be the actual number of CNOT gates. We'll see what happens. What happened there?
You haven't done the set above it first.
I didn't press that one first. Yeah, there we go. Okay. And one thing you'll notice is that this goes quite a bit slower because I'm actually extracting the circuit every single time rather than just counting the number of edges. So this becomes the kind of thing you want to do on some more serious hardware for bigger circuits. So now let's look. And now the thing that's getting reported is the 2-qubit score. Okay, so the number of 2-qubit gates. We started with 67 in our circuit, and then we go through. And by the time we're done, we have 40. Okay, so now if we look, oh, I don't know why that says 67 there. Never mind. Ignore that 67 number. I don't know where that came from. But we started with 48. And then teleport reduce gives 44. And our annealing with this better cost function gives 40. So actually now we're doing the best that we've ever done on CNOT counts for this particular circuit. Okay, so that also ran relatively quickly. Okay, I'm running this on my laptop. I did a bunch of benchmarks on Duvel, which is our big compute server, and I'll show you the data now. But maybe this is a moment I could pause and see if anybody had any questions about the technique.
So it seems to have reduced the T count as well. Is that right?
That's probably a fluke. Yeah, so the reason this happened is I'm actually throwing away some local gates on the inputs and the outputs. So that's actually a
okay.
That's an implementation detail. It should not affect the T count. No.
Right. Okay. Thanks.
Any other questions?
Have you played around with different optimization type algorithms aside from annealing?
No, not yet. I mean, I think there's a lot of things you could do with with learning or genetic algorithms, or I mean, you know, there's kind of a whole bag of things you could throw at this, because effectively there is just this cost that you want to optimize over.
Can I ask a question about the cost function?
Sure.
Could you remind what is the cost of doing the extraction every time?
You mean the complexity theoretic cost?
Yeah. How do
Um,
you quantify how expensive is the extract circuit function in the cost function?
I believe it is worst case cubic complexity
In the qubits.
in the spiders, which is
In the
effectively
spiders.
the gates or the T gates, let's say.
Okay, I see.
So it can be quite heavy. In practice, it doesn't tend to be that bad because it hits this worst case if the thing gets to where kind of everything's connected to everything.
So random circuits, for example?
So with random circuits, I still think it's not too bad. I think the worst case would be random ZX diagrams,
Okay.
which then just happen to be extractable. I mean, almost none of them would be extractable, but if you
Yeah.
did have one that you happen to be able to extract,
Yeah.
I think that would be kind of the most expensive.
So it's just the number of spiders. It doesn't matter how many legs they have.
Well, the number of legs they have is bounded above by the number of spiders. So
yeah,
so
that's
that's why you
right.
get this kind of cubic thing because what one of those instances is putting a bound on the arity of any particular spider.
Okay, yeah. Thanks.
So I was wondering about the annealing process, where so now you've got your cost function be the actual thing that you're trying to optimize. Do you still always take the thing that you end up with after the 500 iterations? It seems like it would be fairly easy to build in a thing where it double checks that it hasn't found a lower minimum anywhere along the way.
Yeah, it always takes the lowest one that it ever found.
Right. Okay.
So here it found 40 at 335. And then by the time it was done, it was at 47. So actually it grabbed that 40. So it always remembers when it found the best thing.
Yeah.
Aleks.
Yeah.
If I remember correctly, calling the basic optimization routine after extraction usually decreases a gate count as well. So wouldn't the honest cost function be extract and then apply the basic optimization and return that number?
Well, we could try it. I mean, it might go really wrong, but let's see. Oh, it actually did better.
Was it 38? Oh, 35.
Now it's down to 35. This might be what I'm actually doing on the big benchmarks. I can't remember if I'm doing it this way or not.
Also, a related remark. A while back, I did some experiments with basically the same idea, but then only working on Clifford normal forms. So Clifford normal form and apply local complementations and then extract and see how many 2-qubit gates you get in extraction. And I also used simulate annealing to do this. And what I found was that it worked really well on low qubit counts. So if you have less than, say, 10 qubits, it works really well, but it drops off quite rapidly as you go to the larger circuits. Where like I only got like a 3% improvement on like random 20 qubit circuits or whatever. So I'm wondering, like, do you see this as well for these circuits, that like if as you get more qubits, there's less of a benefit?
I'm not especially, no, but actually, I mean, when I show the benchmarks, we could see if that's actually showing up. So this tends to behave quite differently for random circuits versus these benchmark circuits. So I started playing with random circuits and its behavior is a little bit wild. But this tends to behave quite well for, I think, classical oracles, or some of them. I mean, this might actually be a natural time to switch to the data. unless other people had questions.
I had one more.
Okay, yeah.
So do you find like the same type of number when you run those more often? Or like maybe run it twice and see if you can find 34?
I mean, you can. It's a bit unstable, like a lot of these kinds of things. So you can maybe find something a bit better if I take 10 random instances and then I compete them all against each other and this sort of stuff. But yeah, I don't have a real good feel for this parameter space yet. So I think there is quite a lot of space for
Yeah,
for
there's
doing-
many tricks you can do for simulate annealing, like parallel tempering.
Mhm.
Where you have something like you said, where you have a bunch of instances at different temperatures, and they don't compete. You just every once in a while you shuffle them around. So you take a sample which has been annealing at some temperature and you randomly jump it to some of the other temperature, and you switch.
Oh.
And then mixing these samples around like that makes things converge faster, apparently.
Huh.
But I've seen this in condensed matter. I don't know how it behaves in this thing.
Is there any particular reason for that, or is that just something that they've seen empirically?
I can ask that. I'm not enough expert to say.
I would expect that you're like when you are walking around at a particular temperature, you're actually basically exploring a little bit of your entire space. And when
Yeah,
you
that's
have
the idea.
multiple
Yeah.
temperatures, you have multiple spaces, and then you shuffle those around and see if something
Yeah.
would happen there.
Ah, I see. So
It's
it's a
like
way to like
giving,
move very far
Yeah.
in your, say, your temperature 12 space. One way you can take a very big move is to pretend your temperature is 5 for a little while and then come back.
Yeah, intuitively, it's like having access to configurations at extreme temperatures more
Mhm.
often.
Huh. Interesting. Well, yeah. I mean that's there's all sorts of stuff you can do. If people want SSH access to the compute server to start playing around with this, that's also something we could talk about. Okay, so the data. Here's what is this? 35 some circuits, and now these are 2-qubit counts: original, teleport, reduce, full reduce, and the sparse full reduce. So this is the one using the actual CNOTs as the cost function. And if I compare these things, first I look at improvement of full reduce over the original, and you see actually full reduce most of the time gets it wrong, sometimes very badly. So 250% increase in CNOT counts. Every once in a while it does quite okay. On this adder 8, it reduces at 36%, which is quite good. I think there's a reason for that John was telling me about. Is that true, or am I making that up?
A reason for that it does badly, or
that it actually does quite well on the adder 8 circuit?
I have no idea.
Okay, then I think I must have dreamt that. Okay, so that's the improvement full reduce over original.
Maybe it's because it reduces the T count by a ridiculous amount, and that's why it can make a much simpler circuit.
Oh, that actually could be, yeah. So it could be that this is a really good reduction in T count.
You should plot improvements of CNOT count versus improvements in T0 count. That might be a useful indicator.
Mm-hmm. Well, so something that kind of washes that out is if you compare full reduce to teleport reduce, because they do the same thing to the T counts. And you see, actually, so the full reduce even does better than the teleport reduce, somewhat curiously. But you see that aside from that, the story is actually getting worse. now, because teleport reduce always decreases the T count, right? So this column is always at least for these bad ones, it's always going to be even worse or the same. And then here's the first sparse one. So this is now sparse reduce over O. Okay, and you notice some green starting to appear here. So this is not a kind of one size fits all solution for CNOT count, but you notice that there are some chunks where this sparse reduce is reducing the CNOT count, and for a few of these quite dramatically. So this one's a 50% decrease in the CNOT count. And if I look also even at the improvement of the sparse reduce over the teleport reduce, the story is actually pretty similar. Okay, so this quite dramatic one is still quite dramatic. This could be one of those instances where actually all the savings I made here was by reducing the T count, because here when I compare to the teleport reduce, I'm actually doing a bit worse. And I think is that everything I wanted to say? No, there's one more column. Now here I'm comparing how much better the sparse reduction did versus the full reduction. Okay, so how much did we gain by doing this annealing on top of the full reduce? And you notice, I mean, it's always some savings. Only this kind of one-off, this QFT thing did almost nothing. But a lot of these savings are quite dramatic over the full reduce, right? And I mean, I guess in light of John's question, we could see how these numbers compare to the qubit count. But you should see, I mean, some of these circuits I think do have 20-some qubits, and we're still getting some pretty significant savings here. So
yes, but if you look at the top 10, top 3, top 4 at the bottom of your screen right now, you can see that top 3 has like a 40%, top 4 is 35%, top 5 is 26%, top 10 28%. So the improvements decrease with like the larger the circuit gets. No, at the bottom, like not the Barenko maybe as well, but also at the top, like line 32, 33.
Let's see. Oh, these ones.
Yeah.
Yeah. Ah, yeah. So 40, 35, 26. But then the top 10 goes back up to 28.
Yeah.
And there's a similar thing happening here, which is 16, 28. Oh, no, this one's a bit more random. 16, 28, 12, 20. So it seems a bit unstable, but it could also be that I'm just not running the optimizer for long enough to really see the true behavior of the thing, if there is such a thing.
So Alex, did you beat any record?
That's a good question. I haven't really dug into that yet. So I would be interested to look at these mod 5.4 circuits, also because it's very small. It would be interesting to see if anybody has a 14 T count realization of this circuit anywhere. But that should come with a bit of a caveat, which is that the outputs of this sparse reducer have not been verified yet. So I mentioned there's this thing about how I'm throwing away some local gates at the input and output. So that stopped me from running the verifier on these things to see if they're actually right. And that's obviously something that's quite important to do before claiming that this is the real performance of the thing, if it's just spitting out totally different circuits or something. But this is a work in progress. So that's where I'm at.
Cool.
Other questions?
So you just so here you just consider the to reduce the the number of CNOT, or you also want to consider both the T count and the CNOT?
So this doesn't change the T count.
Uh-huh.
So this full reduce stage applies all of the T count reducing tricks that we have. So this next stage is all about the CNOT count.
So I don't know. So I just wondering. So if you typically if you want to compare your results with other results, so do you need to consider both, or you can just consider the CNOT? Is there a balance there?
Well, I don't think you're really trading off these things against each other. So I think this is in a kind of a regime. If you decrease the CNOT count, you'll probably end up reducing the T count once you run the circuit optimizer, the basic optimizer on it. And similarly, if I reduce the T count, I'll probably reduce the CNOT count some more because there's just now less T gates in the way.
But if you use for example, if you use phase gadget for reducing the T counts, so probably you increase the CNOTs.
Yeah. So that's kind of what you're seeing in this. In these first two columns, you see that all of this phase gadget stuff is increasing the CNOT count. That's basically because I'm doing lots of local complementations and pivoting, and not paying any attention to what kind of effect this is having on the CNOT count. And then afterwards, this kind of sparsification step is trying to repair the damage that you do kind of before.
Okay, I see. Thanks.
Aleks, two comments. So the mod 5.4 that does so well. So mod 5.4 is interesting because it's basically a phase polynomial circuit. And if you use the built-in phase polynomial synthesizer that does Matthew Amy's, what's it called, parity network algorithm, that also reduces the CNOT count to quite low, and might be in the order of 14 as well.
Okay.
So it might be that what you're doing here is you're finding a sort of optimal representation of a phase polynomial in your diagram or something.
That could be. So if you have what's effectively a phase poly circuit, then you. Well, I think you're actually just kind of moving the edges around somewhat randomly, and this just randomly changes how the extractor is going to generate CNOTs. So I guess it is just kind of exploring that space.
And then a second comment, like the extractor usually like ends up with some global swaps at the end. Like some, do you count those as like 3 CNOTs each, or do you ignore those swaps at the end?
I think I'm ditching the in swaps, but I mean, well, let's see. No, I mean, I'm calling zx.extract circuit with default arguments. Which I think keeps the swaps, and just spits out the 2-qubit count. I don't know if this function returns a swap as a single gate or as 3 gates, but so I might need to call like 2 basic gates or something on this thing.
Yeah, the 2-qubit count should count a swap as 3 CNOTs.
Oh, okay. So actually, yeah, if you don't care about that, which I think is also fair, to allow yourself to generate your circuits up to a permutation, then you're probably doing even better.
I guess going in the other direction from that, potentially one could consider looking at specific architectures and extracting CNOTs that are allowed in that architecture and using that as your cost function, presumably that would also work?
Yeah, it will. Well, if you want to use our algorithm, as in the one of me and Ariana, that will take quite a long time, because the extractor uses it uses a genetic algorithm to find the optimal placement of the qubits. So if you're using a genetic algorithm in the cost function of an annealing or another genetic algorithm, this is going to take quite a long time. But these newer things like the work of Benoit and some other people might be quite a lot faster. So that could be more suitable for this.
The upshot of this is that you just have to run it once, right? Even if it takes a while, it's not something that you want to keep running every time.
Yeah.
You run it once, there is like a, how do you call it? Like a front cost, something, constant upfront cost.
Upfront cost, yeah.
And then you just found the best circuit and then you're happy, right?
Yeah. Yeah, and that actually, so the way I got this data, so I think all of these are annealing for 5,000 iterations rather than 500. And I ran this on the compute server, and I think I gave it something like 8 cores. So it was doing 8 of these at a time in chunks. And it took, I don't know, 4 hours or something like that, or 6 hours to get this kind of chunk of data.
Yeah, that's not bad, right? I mean, you can pay a day to get 30% decrease in CNOT count in standard circuits. I mean, you have to do it for every device every time, but still,
yeah,
it's worth it.
Any more questions? Let's thank Aleks. I forgot to ask people to thank the speaker after the talk ended. I guess it didn't really end. It's just kind of
right. Yeah.
gone
We went
into
straight into
questions.
questions anyway. So
Here's a clap just for posterity.
all right, thanks everybody. And if anybody's interested in working with this or experimenting with this, get in touch with me. Like I said, I can probably give you some access to the compute server, and kind of show you the things you should be poking with your Python code, and so on, if you're interested.